All right, so we're moving on to chapter 2, area between curves. There's a beautiful book. You can check it out. Have some nice stuff in it.
Help me out this morning.
Gave me anxiety this morning.
So, like we can find the area under a curve, we can find the area between two curves. And so that's what we're going to play around with today. And then once we have that, that opens up some more powerful tools where we're going to do some 3D calculus by sliding and spinning stuff. So that's the week in math. Do some. We are live, yeah.
Are you recording?
We are that too. We have no guests on live yet. Okay. So let's take a couple of relatively simple functions to start with. Let's take f of x equals 1. F1, and then extend down just a little, -1, -2, -3. And let's try this one here would be g of x equals x squared minus 3. And so what I want to do is figure out what this area here between the two curves is. And it turns out everything we've done already is going to help us do that. For example, we played with rectangles as approximating area. And so what we have to do is figure out, in this situation, what's the height of a rectangle look like, what's the width? Well, since the skinny part of the rectangle gives me a little chunk of the x-axis, the width of that rectangle is just going to be our delta x. The height of the rectangle, well, that's just the distance from here down to there. So from the blue function down to the red function. So the height here for this one is just going to be whatever the value of f of x there is, because it's the top one, minus g of x, because that's the bottom part. Okay? So that'll give me the distance from there to there. In this case, that's going to give me 1 minus, parentheses, x squared minus 3. Which is 1 minus x squared plus 3, or you could call it 4 minus x squared. And that's for any rectangle between these two functions here. So then we can use our Riemann sum and approximate the area with the sum as the height. Now we have to pick some magic x value, xi star, inside each interval, square it, take it away from 4, multiply by our delta x. Now here I'm going to go from where they intersect, so I can be a little bit more specific about my delta x here. Turns out they intersect at x equals -2 and x equals 2, if you do the math. So the width of each rectangle is 4 over n for n rectangles. Went all the way from -2 to 2 with n rectangles. So then 4 over n. And I'm not worrying about left endpoints or right endpoints or whatever, just some x value in the middle. This is the definition, right, of the Riemann sum. Couple hard parts, you got to come up with a formula for your x values. We've done a whole bunch of those, and then try to evaluate that. Now, if we take the limit of this as n goes to infinity, what do we get?
The definite.
We get the definite interval, yeah. So that's really what we're going to be working with, right? So the bottom line is anywhere you can set up a Riemann sum for a problem, you can turn it into a definite integral. So let's do this one more time and turn that into a definite integral. So I'm going to draw that quick. Oops, wrong button. Go. F of x there. I'm going to switch colors. I've got my g of x there. So this time we're just going to redo this. We're just going to skip over the Riemann sum and see if we can just create the definite integral. So to find the definite integral, you need to be able to identify a height. How do I find the height here? It's just f of x minus g of x. Okay, which function's on top? Well, it's f of x. Yeah. So once you find the height, then you're ready to do your Riemann sum. And then the width is just going to be a dx instead of a delta x. Okay. So the height here is still just f of x minus g of x, just like the Riemann sum. Cleaning that up, we got x minus 4 minus x squared. So then we get that the area is the integral, and here I'm going from -2 to 2 again. -2 to 2 of my height, 4 minus x squared. My width is now called dx.
So when I was reading the book,
yeah,
they throw in absolute value.
Yeah, we'll get to that.
Okay.
Yeah. That's the same idea about net area versus total area that we dealt with before. Yeah, we'll look at that. So we can do this, right? What's the antiderivative for 4?
4x.
4x. What's an antiderivative for x squared?
1/3 x cubed.
Yeah, 1/3 x cubed or x cubed over 3, whichever your preference. And then we need to evaluate that from -2 to 2. So then I'm going to get 4 times 2 minus 2 cubed over 3, and then take away parentheses 4 times -2. Oh, hang on. Shift. Have a pen. There we are. Okay, so let's see, where was that? Minus parentheses -2 cubed over 3. So let's see, we gotta be careful with our signs. The first part's not too bad. I'm gonna get an 8 minus 8/3. Now over here, I'm taking away a negative number, right? So that's gonna be a +8. And then in the next part, I'm taking away a subtraction of a negative number.
So negative.
So it stays negative. That's going to be minus 8/3. So that's 16 minus 16/3. 3 goes into 16 5 times. 16 minus 5 1/3.
Yeah.
5 and 1/3. That bar, which would be what, 10 2/3, I think?
Yeah, 11 minus 1/3, 10 2/3.
I think that area is 10 2/3. Kind of geometric approach to test that out. It's 4 across there, and it's 4 down to there. So if we threw a triangle inside here, that would underestimate the area. Triangle is 1/2 base times height. So 1/2 4 times 4 is 8. So the area ought to be bigger than 8 by just a little bit. And yeah, that looks okay to me. It's in the ballpark. Hopefully it's right. So the area between curves isn't much different than the things we did before. We do need to be more careful about drawing pictures. right? Sometimes you might have been asked to find the area under a curve and you just maybe wrote your integral down without drawing a picture of it. Here, if you don't draw a picture of what you're doing, you may not get the right area. Yeah.
Okay, and so even though some of that area is under the x-axis, it's all still positive.
See, that's the key. Here, the x-axis is kind of irrelevant because the bottom line is all I really need to know is the height.
Okay.
And the height is just always going to be the top function minus the bottom function.
Okay.
And it doesn't happen to matter where the x-axis sits in between there.
Okay.
Okay. All right, so just kind of double check that idea. You know, suppose I had some rectangle and the height was sitting over here at -1, and then down here the height was, say, negative, the next x value was, or y value, sorry, was -5. So we want to know what's that height right there. Well, the height would just be the top number minus the bottom number. -1, that's going to be +5, which gives me a height of +4. Yeah, so as long as you have always the upper number minus the lower, it's going to work out fine. So that's why I mentioned you got to draw something weird happen. Oh man, Google just crashed on me. Part of it. Oh, did I lose my video? Video seems to be still going. Interesting. She never got there, so maybe she's just watching it. It's possible to watch anonymously. All right, let's get my open math back. Yeah, so that's the key I mentioned about drawing the pictures. You draw the picture so you can get upper minus lower correct. Okay, so let's try another one.
And that makes it harder if it straddles the x-axis.
Yeah, it doesn't matter whether it straddles the x-axis or not. So before we had a positive x value and a negative x value. As long as we subtracted in the y value, a positive y, negative y. As long as we subtract in the right order, always upper minus lower, it works out fine. Just like right here, if they're both negative, as long as it's upper minus lower, it works out. So again, that's why the picture is important, so you can identify what's the upper function and what's the lower function. All right, new page. How about f of x equals 1/2 x and g of x equals the square root of x. And what I want to find is the area contained by these functions. So contained is the emphasis. Get yourself a picture of them. I'm just going to freehand mine. Square root of x, or let's do 1/2 x, that's nice and easy. That one goes up 1 over 2, and up 1 again.
Ruby says it's bugging out. Hers is in Spanish.
Cool, she must have set her browser to do Spanish. There is somewhere a place to change that.
So.
All right, so here is my f of x. All right, so that's 4, that's 2. Square root, let's do that in red. Square root has the point 1, 1, and then 4, 2. Oh, look at that, they meet very nicely there. And it's got a point like right there. Okay, so there's g of x right there, and blue, that one's f of x right there. Okay, so nice things about graphing them is my shoes are untied. Did you ever buy a pair of shoes and the laces will just not, they won't stay tied?
Yes.
These
shoes.
I need to get a new pair of laces because these, even if I double knot them, they eventually loosen themselves up. It's like they're coated in silicone or something. Okay. So contained. There's area in here between, but since both of these go off to infinity, there's no containment. They spread forever. So as far as the area contained, that is only this sliver right there. That's the area contained. Okay. So note this stuff out here
is not contained.
Will the integral try to like?
Well,
would be
if you
able
set
to-
the boundary out at 5 or 6, that means you're grabbing stuff outside the containment field.
Okay,
Yeah, so there's only one containment field
but
right there.
it'll still,
You have to choose where to start and stop. That's why you got to graph it.
it'll calculate the area though, not, even if it's not in that containment field.
You have like a sine function and a cosine function like wrapping around each other.
Those, yeah, so if I said find the area contained by the sine and the cosine, those go on forever, right? So you could just say, hey, that's infinity. You don't have to do any work, right? But in this case, the containment is just this part right here, not out there. So there will be some questions you'll see that find the area contained by these things, which means there's got to be a bounded region somewhere. And there could be more than one. We'll look at another place in a minute. There's more than one containment area. Here, there's only one. This is not contained because it goes on to infinity, right? That's not contained. So I want this area right here. Well, if I want this area right here, what x value should I start looking at?
0.
And what x value should I stop looking at?
4.
Yeah, and that's important. You need to identify those boundaries, okay? Now, next thing we need to identify is the height, right? So to do the height, I say, okay, I'm going, as x goes from 0 to 4, so I'm just going to draw some vertical line in here. So there's a little tiny rectangle right there. That little tiny rectangle right there has a width of dx, according to the definite integral. And how do I find the height of that rectangle?
G of x minus.
Yeah, in this case, the height of that rectangle is g of x minus f of x. So it's not always f minus g. It depends on the situation. Okay. So for us, let's see, what's my g? My g is the square root of x, and my f is 1/2 x. So this area right there has to be the definite integral from 0 to 4 of the square root of x minus 1/2 x dx. So now that I've set up the integral, I just find an antiderivative, if possible, and plug in the boundaries. So you guys finish that, and then I'm going to show you something else cute about this one.
Did you have a third function like?
We'll do one today with 3 functions.
Sounds that equals 5.
Yeah, you could have a third function involved, yeah. Or a fourth or a fifth. It could be a lot.
Yeah.
Which you could have as many functions as, yeah. There's no limit. We're going to probably not do any more than 3 functions at a time.
How do you tell which one you subtract first? F(x) minus g of x.
It's always the up, because you want to get the height right. It's always the top number minus the bottom number.
Okay.
And in this case, g of x is always on top.
Okay.
The problem comes is, what if they switch? Who gets to be on top? Then we have a problem.
Is that where you do that?
That's where you do the absolute value. Yeah, we'll do one of those in a minute. Okay, so come up with this value here.
So area integral from 0 to 4. Oops, got carried away with my square root there. Square of x minus 1/2 x dx. Now usually I don't remember the direct antiderivative of the square root of at the top of my head, so I usually rewrite it as x to the 1/2 power. So add 1, that gives me x to the 3/2 multiplied by 2/3. And then x squared over 2, so that's going to be a 1/4 x squared. Square root of 4 is 2. 2 cubed is 8. So this part is, I believe, 16/3. 4 squared is 16, divided by 4 is 4. 4 would be 12/3. So I think I get an answer of 4/3. Or 1 and 1/3 if you like mixed numbers. Let's get that. Couple nods. Is there anything wrong with plugging this into your calculator? No, but every once in a while I'm going to ask for an exact answer, so just keep that in mind.
So I believe the answer is 1 1/3. Carter, question?
Desmos actually lets you turn decimals into fractions now.
It does let you do decimals to fractions?
Yeah.
There's a function for it, or
No, like
there's just a button for it now?
on the phone right here.
Is it only on the app?
Well, button revolutionary.
Yes, I better open Desmos and see.
I need this.
Right there.
All right. Fun
Oh,
with
yes.
calculators.
Here.
Desmos has a
Oh,
decimal to fraction feature, so let's see.
Right here, that little button.
My original functions
Oh, my
were
goodness. Bless
f of
us.
x, oh, the excitement.
Over one little button.
This is the best thing for napkins.
All right.
I
Now,
did something.
I'm gonna make a function called a of x,
Yeah, I'd update it.
a for antiderivative. And the antiderivative was 2/3 times x raised to the power of 3/2. And then what? Minus
Minus
1/4 x squared. So the nice thing about having that is not really that the graph is there, but now I can use function notation.
Okay. I was like,
What is a of 4 minus a of 0? Right.
It's right where you're thinking.
And then, yeah, it's
Oh,
right.
and there's a thing hiding over here
Yeah, and then click
that
the.
says, oh, look at that, so beautiful.
Yeah.
Wow. And it just switches back and forth between fraction and decimal.
That's
Desmos, you rock. All right.
Um,
GeoGebra has a trick that's better than that.
Yeah, GeoGebra, just go.
You want to see?
Yeah.
Yes.
Will GeoGebra do
Let's see
this?
if it can.
Sort of.
Sort of,
So this is not a legal thing to use on a test, but you could check your work with it. So if I have a function f of x equals 1/2 x, and I have a function g of x
one of those, like,
equals, what was it, square root of x?
square root of x, yeah.
I want that region right there. Okay, so nice, I love, both tools let you, oh, this one's not doing it. The phone app automatically finds the intersection point, so I guess I have to hit the intersect button here. Anyway, there's this wonderful formula called integral between. You got to get the top and the bottom function right. What's the top function?
G of x.
G, and then it says, what's your other function? F. Where do you want to start? 0. Where do you want to end? 4. And 1 1/3 with almost 1/3. It's a little off there at the end. It's using Riemann sums to do it, probably. So it gives me about 1 1/3. It's not going to give me the exact answer.
So we're smarter than a computer?
Yes, we can give exact answers what the computer can't. However, there is the integral calculator online. I don't know if anyone's checked that out. So just to make sure everyone's on the same playing field. This is not legal to use on a test either.
I only use it to check.
So integral calculator with steps, exclamation point.
Please don't check my searches.
So here you enter,
I promise.
you enter your integrand. So my integrand was what? The square root of x minus 1/2 x. And it pretty types it for you, which is kind of cool. And somewhere here I can go to options and say the lower bound is, or the upper bound is 4 and the lower bound is 0. And look at it, puts them in there and everything. And even better, it will give me a definite integral and it will evaluate the integral. Okay, so this is not legal on a test. So if you just do your homework using this, you're screwed when the test comes along.
Yeah, if you
Not pointing at anybody or naming any names. So you got to work it out by hand too, but this is a great place to go and double check. Problem, if you do your homework and then check it with this, and you got it wrong and you try it again and you check it, you got to at least do 1 or 2 without ever looking at this, because otherwise you get to the test and like, oh man, my checker is not with me. What can I do? So please,
This is a color.
don't abuse this. It's a beautiful thing. It's wonderful. It's powerful. I wish this was out when I had calculus, but it wasn't. All right, so I want to take another perspective on this problem. So let's redraw the graphs. 1, 2, 1, 2, 3, 4.
So I had, tracking, right? Go. I had this function there. That was my f. And then g of x did something like that. And we want this region here, right? The contained region. All right. So sometimes it's easier to do a problem sideways. What do I mean by that? What I mean is draw a sideways rectangle instead of a vertical one. If I do that, instead of having a little tiny sliver of x, I have a little tiny sliver of y. I have a dy there. Instead of y as a function of x, I want x as a function of y. Right? The inverse function. So if g was a square root, what's the inverse? A square. The inverse of a square root is a square. So this red function here could be called x equals y squared, if I solve for x. And f was y equals 1/2 x. What's the inverse of that? It would be 2y. Yeah, so the blue function would become x equals 2y. That's a y.
It's a very fat
I
Y.
should have just started over. Anyway, that's a big fat y up there. So then it's just a matter of saying, okay, which one's on top though? Well, here I have x as a function of y, so I'm looking this way for the height.
So we have to look at it that way.
So top is over here, right? Because those are bigger x values, and lower bottom would be over here. So which one's the top function?
Blue.
The blue one, 2y, is the top one, and then the bottom one would be the square root, because that's the bottom of my rectangle in this particular scenario.
Which is opposite.
So that means my height here would be 2y minus y squared. Okay, so let's try this again. We're going to integrate 2y minus y squared with respect to y. And where do we start for y?
0.
Okay. And where do we end for y?
2.
2. Now the boundaries change, so I'm going to write y equals for the boundaries. All right, so let's see, what do we get here? Antiderivative for 2y?
To y squared.
Y squared. Antiderivative for y squared?
1/3 y cubed.
1/3 y cubed. And we're just going to do that from 0 to 2, which is going to give us, let's see, 2 squared minus 2 cubed over 3 minus a bunch of zeros. So that would be 4 minus 8/3. See, 3 goes into 8 twice. With 2/3, with, let's see, 2/3 left over? Yeah.
Yeah.
If I take 2 2/3 away from 4, I get 1 1/3, which is the area we got before. Okay. Now, turning sideways is a big mental leap because we're used to doing it the other way. So that's going to take some getting used to. Okay. So I was emphasizing drawing pictures before. You really got to draw pictures when you go sideways and double check you're getting stuff right.
So on the question on the test, we have to do that.
There are some problems that are way easier to do sideways. There are some problems that are impossible not to do sideways.
Oh, very tricky.
Okay. It just depends on the functions that we have and the picture. Okay. So we'll do a couple other examples. All right. Question, Vitor?
Yeah, couldn't you not reflect, like, move it, put it straight forward, and just
Do what?
like, move the straight line to the straight line, moving the x-axis, then
Rotate the whole thing?
yeah, rotate the whole thing so it's flat.
Yeah, so rotating is pretty complicated. So if you did, so you're saying rotate through that angle
Yeah, rotate.
to flatten out that line? Yeah, so then this function is going to get way more complicated when you rotate it. Yeah, so what you'll
Just
you'll
pretend
get,
to rotate it in your head.
so this is a chunk of a parabola, right? So the general form for a parabola at any angle, not just a vertical or a sideways parabola, but an angled parabola, looks something like, let's see if I can get this right, some constant times y squared plus some other constant times y plus some constant times x squared plus some constant times x plus some other constant times xy plus maybe another constant equals 0. So that's kind of the general form of a parabola. So if you rotate this, that means, so for us, for the x equals y squared, most of those constants were 0 or 1, right? Which is nice. If you rotate it, most of those will be non-zero. Yeah, so there are times where rotation does make the problem easier, but there's sometimes rotation makes it harder. But it's an interesting thing to think about.
But there is no other way to represent the parabola.
Yeah.
It's a different line. Like rewrite the equation.
There are other coordinate systems you can choose, but we don't want to get there today. Next quarter we'll do that. Yeah, we'll look at polar coordinate system next quarter. All right.
No, sure.
Okay, a couple more examples before we run out of time. All right.
32.
So f of x equals x cubed minus 3x squared minus x plus 3 g of x equals x squared minus 2x minus 3, and we want to find the area contained by these two functions. So get yourself a graph of them.
Will you expect us to write?
Do you want us to draw the graph of that, or?
Get it on a computer graphing system.
On the test, will you expect us to draw the picture?
Yes.
Okay.
I will.
Do you go start the book when you make your notes?
What's that?
You just read a book, you go off the book, and then.
You just asked if I take notes for class based on what's in the book, and the answer is yes.
That's a cute one.
That's not
that
what
is
I
a-
wanted to
So we
share.
can just do the same thing we were just doing, just twice with the different.
Yeah, because it switches on us. So this is one of those problems that switches. So let me catch up to y'all. Screen, save.
Zoom out.
All right, so
Ew.
f of x
Oh, that's nice.
equals x cubed minus 3x squared. Well, I worked hard to make sure these intersected at nice places.
Oh, thank you.
If I just randomly picked a cubic and a parabola, they would not intersect
They
at nice
intersect
places.
it. Fantastic places.
Yeah.
Yeah, I appreciate that.
Do we have to draw it real quick?
Yeah, we're gonna do a rough sketch of it on paper.
Okay, let's start that, guys, while he's
Yeah.
doing that. he gets to copy and paste it from like screen.
I know. I'll draw it by hand too. G of x equals x squared
Repeat the line, X.
minus 2x. No. Equals. No. Minus. There we go. 3. Did I get that right? What you guys got?
Yeah.
I don't like the red and the orange though. Can I make you
If you click on the line,
on it,
and then there's the-
color change. Okay. All right. So we've got a couple of different areas, and the problem is F is on top as I go from -1 to 2, but then it switches. Then G gets to be on top from 2 to 3. So this is what Sam was asking about absolute value. Since I'm trying to find the contained area, it doesn't really matter what function's on top necessarily. I want this area over here, and I want that area over there. If I try to do it in one integral, I will not, they'll cancel each other out of it, and I won't get the full area, right? So we've got to do this in 2 integrals, which means I need to know where they intersect. And mostly the problems are chosen so the intersections are relatively easy to find. Okay, so I'm going to try to draw that. I sketched it on my paper, but I didn't.
So again, having the computer algebra, the computer graphing thing is very helpful. So let's see, the red one has -1, 1, and 3. -1, 1, 2, 3. So that thing goes up, and then it comes down a ways. How far? Not too far. And then it goes up again, something like that. The blue function goes through there, and somewhere over here. So the blue function goes there, there, and there. So it does something like this. Okay, so that happens at -1, that happens at 2, and that happens at 3. Labeling these guys, F is red, G is blue. Okay, yeah. So to find the first area here, F gets to be the top function. So I'm going to first integrate from x equals -1 to 2 of f of x minus g of x dx. And then I want to add on to that the integral from 2 to 3. And now g is on top in that region. So that's going to be g of x minus f of x. And the cool thing is once you do the first subtraction, the next one's just the opposite of that. So it's not like you have to re-subtract to figure that out. All right, so let's see. I'm going to go to a new page now that I know this. So we need to have the picture so we can figure out what the bounds that we're graphing on to get the contained area.
So we're adding the top one to the bottom one?
We're going to add the top one to the bottom one. Yeah. So here's what I get. For the first one, the integral from -1 to 2, I got x cubed minus 4x squared plus x plus 6. Anyone else get that?
I got that.
Okay. And then the next one is just going to be the opposite of all those terms. So we're going to add on to that the integral from 2 to 3 of -x cubed plus 4x squared minus x minus 6. Antiderivatives are going to be pretty darn similar. We just switch a sign here and there. And at this point, calculator is a beautiful thing. My GeoGebra graph. Oh, I put it over there. So I'm going to make a function called a of x, which is my antiderivative function. And that was, again, let's see, x raised to the 4th for 4 minus 4/3 x raised to the 3rd plus x squared over 2 plus 6x. Want to go through any antiderivative? I think that's right. Yeah, so once I type that in, I can say, all right, the first part is just going to be a of
2 minus a of 1. No,
Negative.
negative 1. So the computer tells me it's 45/4, which is 11.25. And then for the next area, I have to take the opposite of this stuff. So that's going to give me the opposite of my antiderivative, evaluated at 3, and then minus the opposite, which is plus, oops, a of 2, which is 7/12. All right, so what was that again here? 45/4 and 7/12. What did I just do? Didn't want to hit that one.
I got 45/4 and 7/12, and Desmos now will do that fraction arithmetic for you. It's so sweet. And 3 times 45 is what, 135? 42/12. I think.
And that should reduce.
145.
Just 71/6.
Okay, and that reduced to 71/6. 6 goes into 71. Let's see. 1, and 5, 6. 11.83-ish.
Yeah.
Okay.
Cool. We did it. All right. Hey, remember that cool feature GeoGebra has? Will it work here? No, the integral between. Integral between. It wants to know what's the top function. Oh, that switches, so I can't do it in one shot. I would have to do it in parts again. Yeah. And it would give you approximately the right answers. If you did try to do it in one shot, you'll end up with a problem. Watch. So let's say I take, yeah, F's usually on top. It's good enough. Go from -1, 3. Then I'm going to get some cancellation. Notice I lost a bit. And what happened is the 7/12 got taken away from the 45/4. So I'm off 2 times 7/12 because it got taken away instead of added on. So you just got to be careful about that. It's cool that it draws the shading, but it's not the area I wanted because this part's positive and that part's negative. So you got to be cautious about using technology. It does exactly what you tell it to do, which isn't always what you want it to do. All right, another cute problem. New page. Function f of x equals x squared. G of x equals 2 minus x. And y equals 0. I want the area contained.
Y equals 0?
Yes.
That mean x squared?
We could call that h of x if we want. So these are my 3 functions right there. So if I graph this, x squared does something like this. Best of my ability. 2 minus x starts up here and then drops down like that. And then y equals 0 is right there. So the area contained here is this funky, almost triangle-looking thing, is the area contained by these 3 things. All right. Cool. Couple ways to do this. One way to do it is our usual way by saying, let's make a slice like this, in which case I have a dx there. Which function's on top? It depends on which part of the figure I'm in, okay? So from 0 to 1, let's see, f of x is on top, and 0 is at the bottom. From 1 to 2, g of x is on top, and 0 is at the bottom. So one way to do this would be the integral from 0 to 1 of x squared minus 0, which is just x squared, plus the integral from 1 to 2 of 2 minus x is the top function, 0 is the bottom, but if I subtract 0, nothing happens, dx. So that's one way to get the area. Anybody want to suggest another way? Excellent idea, Peter. You were speaking to me.
We get that checked out.
I will. So here's just a re-sketch of that situation down here, right? That's this place I'm trying to find. What if instead I let my rectangle go sideways? In that case, I would have a dy. So if you have a dx, you write your functions as y equals stuff with x. If it's a dy, you write your things as x equals stuff with y. Okay. So what would this blue function be? So the blue function is this one. So we start off, oops, let's make it blue. Y equals 2 minus x. To solve that for x, I could just add the x to the other side. X plus y equals 2, then subtract the y over. X equals 2 minus y. Oh, cool, almost the exact same equation. Yeah, this function right here
Is the square root.
is just the square root of x. Yeah, so on this side we have the square root, not square root of x, but square root of y.
So y.
And on this side over here, we have 2 minus y.
And then. how do you-
And now here, I can just integrate as y goes from here to there, right? Because I need this rectangle to start down here and then go up that way. So y is going to go from 0 to 1. Yeah, 0 to 1, according to this picture here. So another way to find this would be the integral as y goes from 0 to 1 of the upper function, 2 minus y, minus the lower function, square root of y. dy. And either one of these, if I set them up right, it's going to give me the exact same area. Shouldn't matter how I set them up. dy. Oops, I said dy, but I wrote an x. Either one's going to give me the same exact answer. So hazard on one side. You got to figure out where the break is, figure out which function's the upper one, put them all together into at least two different integrals. Other way, you got to think sideways, which stretches your mind a bit. There are going to be some problems where you're going to want to think sideways because converting the other way is such a pain in the butt. So we're just about out of time for fun with math. We'll do a couple more of these tomorrow, and then we should have a little time to break into volumes, which is a very similar technique to these areas. Yeah, so we're going to break into 3 dimensions, which means sketching things is going to get a little bit tricky.
Wouldn't g of x cross back over with x right there and you have another enclosed area? There's like a parabola of the right side.
On the left over here,
Yes.
I need all 3 of these to be the containment. So you're thinking about this region up here?
Yeah, like with that is anything.
Yeah, because it doesn't include y equals 0 in terms of containment.
I'd be disappointed if-
Yeah, so the only part it's fully contained by all 3 is right here. Yeah, and that is a little tricky to figure out. What is the containment area?
This
It's this fall, technically.
A shoelace.
This fall, right?
Yeah, same
The
problem.
next coming fall is this fall.
It's currently winter, Vitor.
No, I'm